All right, so this is our first video on energy conservation, the energy conservation law, and this is when energy is conserved. And as you can see, the energy one or the mechanical energy one equals the energy two out. Okay, one and two is just going to be classified as this. So if it's one, that means before, and then two, that means after. Okay, so my energy before equals my energy after, and that's what the energy conservation law when energy is completely conserved. So if I have a ball here, whatever potential energy I have here, that exact same potential energy is going to be converted into kinetic energy. Okay, so if we derive the equation, this is what we're going to find. So the energy before equals the energy out. So what that means is that whatever potential energy I have here is going to convert and turn into kinetic energy here, and it's going to be the exact same amount. Okay, so let's go ahead and solve for it. So in class, we learned that mechanical energy, or E, is just your potential energy and kinetic energy added together. So the energy before is going to turn into K E 1, kinetic energy before, plus P E 1, potential energy before. And the same thing goes for E2. K E 1, 2 plus P E 2. Okay? So this is my mechanical energy before, and this is my mechanical energy after, just a little bit more in detail. All right, let's get in more detail. So I know the equation for kinetic energy is 1/2 mv squared. Now this velocity is special because this is the velocity before. So I'm going to subscript it, or I'm going to write a 1 there to represent the velocity before. Plus mgh1. All right, because that's what potential energy is. That's the equation for potential energy. And this height represents the height before, which is 1. Okay. All right. So the same thing I'm going to write here, except I'm going to replace all the ones with 2. So it's going to be 1/2 mv squared 2, the velocity after, plus mgh h2, the height after. Okay, so now let's go ahead and go back to our picture, and let's see what crosses out and let's see what stays. Okay, so if we look at our picture, the ball is at rest. So the ball is at rest, that means the velocity is 0. And this is the velocity before, right? So if this velocity here is 0, this whole thing goes to 0. Okay? And the mgh1 comes back down. Okay? Now, as the ball starts to fall after, the velocity is no longer 0. It starts to increase, right? Because I'm increasing in kinetic energy. That potential energy here is converting and changing into kinetic energy. So the only thing that is decreasing is my height, and that height is going to go to 0. My height after is going to be 0. So if we look here, this is going to turn into 0 because anything times 0 is 0. And I keep this 1/2 mv squared 2. All right. And this is now 0. All right. So now this is the most important part of the energy conservation law when everything is conserved. What I'm about to show you pretty much says that if I know the height of something, I could tell how fast it's going to be once it falls. It also says if I know how fast something is, I can tell how high it was before it fell. Okay, this is the power of this equation. So first of all, I'm going to get rid of my like terms. So I have a m on this side and an m on this side. So because these two m's are the same, they cancel out. They go away. We know that these zeros are already gone, so I don't really care about these no more neither. So let's rewrite what I have left over here. I have G H1, which is G times H1 or G times H, equal to 1 half V2 squared. Okay? So with this equation, we're going to derive two equations. We're going to derive the height before, and we're going to derive the velocity after. So let's first do the height. So if I were to divide this G on both sides, if I were to divide this G on both sides, the equation for the height before will equal 1 half times the velocity 2 squared over G. And what this equation says is that if I know the velocity after, I know the acceleration due to gravity, I can figure out how high that object was. Okay? So when this object fell here, it came with some type of velocity. Okay? If I know the velocity after and the gravitational pull, I already know that. That's given, right? I can figure out how high it was. All right? That's the power of this law. This law says that if I know how fast something fell, I can figure out how high it was. That's pretty cool. Okay? Now, the second derivation is going to be the opposite. It's going to tell me if I know how high something is, I could tell how fast it is going to be when it comes down. So then that equation is just going to be 2 times H1 times G, and all of that is square rooted. All right, and then just to kind of show people how I got that equation, so I started back with where I had H1 equals 1 half GH1 equals 1 half V2 squared. So all I did was solve for the V2. So I had to multiply this 1 half. That became 2GH1 equal to V2 squared. And to get rid of this square, I have to square root both sides. So then it's going to equal square root 2GH1 V2. Okay. Now, that's what this is here. Okay. So what these two equations say is that if I have the velocity after the V2, the acceleration due to gravity, I could figure out how high that object was if it fell. Okay. This equation says if I know the height and the G, I could figure out how fast it is. Now, this is probably the most important one because this is the one that we can figure out to use to find the kinetic energy and see if the potential energy was the exact same as the kinetic energy when the ball fell down. Okay? Now, if none of this made any sense, just make sure you have this written down in your journal and we can talk more about it tomorrow. Okay? But this is the energy law of conservation. Thank you.